Okay, so let's start with two professors. Oh, there he comes. So format is similar. You can come to the front and ask questions. Anybody? Come out and.
I have a question to Professor Van Rees. You talked about the conformal bootstrap in the six-dimensional spoken for field theories. So can we have some useful information other than a central charge that can be extracted from bootstrap in 6D?
Yes, you certainly can. You can do similar things to the things I alluded to in my last lecture, which is you can get bounds on OPE coefficients. You can get scaling dimensions of operators. The representation theory of the superconformal algebra is quite complicated. So you have operators that are long, you have operators that are short. The short guys have protected dimension, but the long guys have unprotected dimensions. And so you can get bounds or constraints for those scaling dimensions as well.
Okay, thank you.
Any other questions? No?
Maybe I should add there are gazillion plots in our paper that you can look at.
I have a question for Professor Bult. When we calculate the correlation functions of a CFT in Lagrangian approach, we incur infrared divergence. But in this algebraic approach, where does that go?
Sorry.
When we if we like in the Lagrangian approach of CFT, so there is infrared divergence. But like if we do in this operator approach, where does the infrared divergences go?
For correlation function of local operators, there's no problem with infrared divergences. The infrared divergences appear when you have massless particle and you try to compute scattering amplitude.
Scattering amplitude.
Yeah, but I didn't talk about S-matrix elements, right? So for correlation function of local operators, there's no problem. These things are just finite. Like you may have to regulate some UV divergences, but we all know how to do that. But there's no infrared problem.
And I have one question from Professor Nishioka. So you said that like.
Can you speak a little louder?
So you said that like just like there is generalized F theorems for the two CFTs at the UV fixed point and IF fixed point, and for QFTs also there are there is something can be said, and you said something about interpolating functions. Can you little bit elaborate on that?
Okay. I think the conjecture, I think it's still conjecture, but basically the F I defined is supposed to be an interpolating function as well. But naively, so there is a depending on the let's consider the relevant operator, the relevant perturbation, to trigger an RG flow from UV to IR. Then depending on the conformal dimension, so F I defined, sometimes when delta is larger enough, then it is a good interpolating function. But when delta is less than some critical value, it is known that it's not a good function. It's not monotonic. But I think the paper by Kiritosis and his collaborators, Kiritosis, I think. Sorry, my pronunciation is not good. So anyway, I can show you the paper later. But okay, anyway, so there is a work. I think it's based on holographic setup, and where they examined the monotonicity of the sphere partition function, and they argue that if you take a Legendre transformation of the F sphere partition function, and then once you take a Legendre transformation, then it is still nice monotonic function, even for conformal dimension is less than critical value. So that's another generalized conjecture. So yeah.
Thank you.
Oh, so I have a question for Professor Van Rees, and so when considering free bosons in 2D, their dimensions are formally 0, and that I guess that happens because the correlation functions for free bosons are logarithmic, and that somehow I remember that people were talking about log CFTs, and are they related? And another question I have is how generic or non-generic are such logarithmic effects?
That's a lot of questions. The free massless boson in 2 dimensions, if it's not a compact boson, so you don't identify phi with some periodicity, phi plus 2 pi, or, is a theory that has continuous spectrum. And I did not really want to talk about such theories because it's a bit complicated. And in particular, the operator phi itself is weird because it violates, the 2-point function violates this idea of cluster decomposition. So it's a bit of a strange theory. I think it's nicer to compactify it.
Okay.
Then phi itself is no longer an operator because an operator should not be 2 pi periodic. So you have to consider things like e to the ik phi, and those are good operators for appropriate values of the momentum. Or del phi, the derivative of phi. That's also a good operator. And all of that, then everything is fine, you have cluster decomposition and so on. So that's how I propose to get rid of the logarithm. I don't want to talk too much about theories with continuous spectrum. Then you asked how generic logarithms are. With the one exception, maybe, well, in theories with the discrete spectrum, they don't appear in 2-point functions. You don't get this logarithmic behavior. You get power loss because of the conformal wide identities. In fact, there's one way in a non-unitary theory that you can get logarithmic behavior in correlation functions, which is if your dilatation operator is not Hermitian, but has some Jordan block structure, like delta, 1, 0. So it is obviously not a symmetric matrix, but if your dilatation operator acts on a pair of operators like this, then if you compute the 2-point functions of this pair of operators, and you just go through the logic of the conformal wide identities, and you compute the 2-point functions, then you'll find that this 2-point function has logarithms. But clearly this is not an Hermitian operator, and so it's a non-unitary theory.
Which might be impossible to explain in a few words. But could you just say explain very briefly how you start from cyberwitting theory to extract to analyze the QCD?
Well, you can't in any straightforward or non-straightforward way go from cyberwitting theory to QCD because the fields in the theory don't transform in the same way under the gauge group. Cyberwitting theory is a theory that only has adjoint fields.
Okay, so adjoint QCD?
You can go to a version of QCD with adjoint fermions, yeah, for instance.
I see.
That you can do by deleting the scalars, basically.
Okay.
By deleting the scalar superpartners of the gauge fields. And so you can do that by some carefully chosen deformation that you can track along the RG flow and so forth. So that's possible, yeah.
But you don't have you don't have non-remutation theorem. So
no, because the moment you do that, you break supersymmetry explicitly by hand, right? You're going to try to lift some superpartner, so you're going to break the supermultiplet apart and give some fields a large mass and keep only a subset of the fields. And without supersymmetry, there's no non-renormalization theorem.
Yes. Oh, okay. So, but I would say that so the potential will be very complicated if you consider the RG flow.
That's right. It'll be complicated and completely impossible to compute, except for very small deformations around the supersymmetric point, perhaps. So in the neighborhood of the supersymmetric point, you might be able to compute it and analyze it. So that's possible.
Okay.